The ISS is leaking air into space. Right now. Not a drill, not a warning. It's happening, and NASA knows it. Parts of it are so old, engineers can't permanently fix what's breaking. And today, astronauts had to evacuate into their Dragon capsule just because of a crack the size of a fingernail. Here's the brutal truth. The ISS has less than 5 years left, and no replacement is ready. But one vehicle changes everything, and it's not what most people expect. Stay with me. This gets wild. Let's start with the numbers, because the numbers don't lie. The ISS has been orbiting Earth since 1998. That's over 27 years in one of the most brutal environments humans have ever encountered. No weather, no atmosphere, just radiation, extreme cold, extreme heat, and the constant threat of micrometeoroid impacts every single day. And here's something most people don't realize. Some parts of the ISS weren't even built in 1998. The Zvezda service module, the backbone of the Russian segment, was manufactured in 1980, completed in 1990. That means certain components aboard the ISS today are closer in age to the Apollo moon missions than they are to your latest iPhone update. Think about that for a second. The hardware keeping 6 humans alive in space right now was engineered before the internet existed. So when people ask why the ISS is struggling, that's your answer. It's not a design failure. It's not negligence. It's simply time doing what time always does, wearing everything down. And the signs are impossible to ignore. Air leaks sound minor. They're not. In space, air is everything. Lose enough of it, and the pressure inside the station drops. Drop the pressure too far, and no human can survive aboard. So when tiny cracks began appearing inside the ISS structure, particularly in the Russian segment, NASA didn't just file a maintenance report. They started paying very close attention. Here's how serious it got. In early June of this year, a major leak event forced NASA to make an extraordinary decision. Crew members were temporarily moved into their SpaceX Dragon spacecraft, not to launch home, but to shelter in place while engineers assessed the situation. The Dragon became a lifeboat parked at the station's door. Let that sink in. Astronauts aboard the most advanced space station ever built used a commercial capsule as an emergency refuge, because the station itself wasn't safe enough to guarantee their safety. Now here's the part that should make everyone uncomfortable. Engineers can patch the leaks. They've been doing it for years, but they cannot permanently fix them. Every repair so far has been a temporary solution, slowing the leak, reducing the pressure loss, buying more time. But the cracks keep appearing. Because you can't stop metal from aging. You can't stop decades of temperature stress from doing structural damage. And in space, once a material degrades, it doesn't recover. The ISS is currently losing air in multiple locations, and the rate is increasing. So who's really at fault here? Russia, the original designers? Or is this simply the inevitable outcome of operating any structure for nearly 3 decades in one of the most hostile environments in the universe? That's a question worth sitting with, because the answer determines everything about what comes next. It's not just leaks. 2030, the countdown. Nobody is talking about. Here's where it gets even more uncomfortable. The air leaks get the headlines, but they're only one piece of a much larger problem. The Canadarm2, the robotic arm that has assisted with virtually every major construction and maintenance task aboard the ISS, has required significant repair work in recent years. This isn't a small system. This arm is the mechanical muscle of the station. Without it, operations grind to a halt. Then there's the visiting spacecraft issue. The Soyuz MS-9 capsule, a Russian crew vehicle, experienced a coolant leak so severe that the spacecraft was deemed unfit to return astronauts to Earth. The same problem appeared on Soyuz MS-22. Multiple Progress cargo vehicles experienced similar leakage issues. These weren't ISS problems directly, but they were problems happening at the ISS, creating cascading risks for the crew on board. And then Boeing's Starliner arrived and added another chapter to that story. But let's stay focused on the station itself for now. The pattern is clear. It's not one system failing. It's multiple systems, across multiple nations, across multiple vehicle types, all showing signs of age and stress at the same time. When you see that kind of convergence, that's not bad luck. That's a system reaching its operational limit. NASA engineers have a term for this phase. They call it graceful degradation. The idea that a system doesn't fail all at once. It slowly becomes less reliable until the cost of keeping it running exceeds the value it provides. The ISS is entering that zone right now. And the critical question isn't whether the station will eventually fail. It's whether humanity will have a replacement ready before it does. The ISS is officially scheduled to retire in 2030. That's less than 5 years away. And here's the twist that most coverage completely misses. Retiring a space station isn't like shutting down a factory. You can't just turn off the lights and walk away. The ISS needs to be safely deorbited, meaning it needs to be deliberately guided back into Earth's atmosphere, where it will break apart and the surviving pieces will splash down in a remote ocean location. That's an enormously complex operation, and it requires years of preparation. So the real deadline isn't 2030. It's more like 2027 or 2028, because NASA needs time to plan, coordinate, and execute the deorbit safely, which means the window to have a replacement operational is even shorter than most people realize. Now add this to the equation. China's Tiangong space station is fully operational right now, and it's actively recruiting America's scientific allies. And China is actively recruiting international partners to conduct research aboard it. The same kind of international scientific cooperation that made the ISS so powerful. If the ISS retires and no American-led replacement is ready, there will be a gap. A potentially years-long gap in which the United States has no continuous human presence in low Earth orbit. That's not just a scientific problem. It's a geopolitical one. And it's exactly why the pressure on NASA and on the commercial space sector has never been higher. The commercial race, 4 contenders, one massive problem. NASA's plan to replace the ISS doesn't involve building a new government station. Instead, the agency is funding private companies to develop commercial successors, and then purchasing access to those stations for astronauts and research. On paper, it's a smart strategy. It spreads the financial risk, encourages innovation, and could produce a more modern, efficient station than anything a single government program could build. In practice, it's messier than it sounds. 4 main competitors are currently in the race. First, VAST, moving the fastest of any commercial station developer. Their Haven 1 module is designed to launch aboard a SpaceX Falcon 9 rocket and operate as a small, standalone station, later expanding through additional modules. VAST has moved aggressively and has SpaceX as a key partner for both launch and crew delivery. Second, Axiom Space, taking a unique approach by attaching their modules directly to the existing ISS before eventually detaching them into an independent station. They've already flown private astronaut missions to the ISS, giving them real operational experience. But their timeline depends heavily on the ISS remaining functional long enough for their modules to reach full operational status. Third, Orbital Reef, a joint venture between Blue Origin and Sierra Space. The vision is ambitious, an orbital business park featuring expandable habitats that launch compactly and then inflate to full size once in orbit. On paper, it's elegant. In reality, expandable habitat technology still has significant development hurdles to clear. Fourth, Starlab, focused on simplicity and commercial efficiency. A large single-module station designed for scientific research and private missions, with a spacious interior and streamlined construction approach. Here's the problem that none of these projects can escape. Every single one of them, without exception, relies on traditional modular architecture, meaning they all launch relatively small pieces and assemble them in orbit over time, which means multiple launches, multiple docking operations, multiple opportunities for something to go wrong. And every single one of them is behind schedule, not slightly behind, significantly behind. Manufacturing delays, testing setbacks, funding challenges, regulatory certification processes, all of these have pushed timelines to the right. And the uncomfortable reality is this. There is a real possibility that the ISS retires before any of these stations is fully operational. That gap, even if it lasts only a year or two, would represent the first time since November 2000 that no Americans have been continuously present in space. Here's something else almost nobody mentions. 3 of the 4 commercial station competitors, VAST, Axiom, and Starlab, are all planning to use SpaceX rockets and Dragon capsules for crew and cargo delivery, meaning even the companies competing with SpaceX's own potential station concepts are depending on SpaceX infrastructure to function. SpaceX isn't just a player in this race. It's the road the race is being run on. Enter Starship, and everything changes. Now we get to the part of this story that most people haven't fully processed yet. When SpaceX unveiled Starship, the conversation was almost entirely about Mars, about deep space, about putting humans on other planets within this decade. But here's the twist. The same characteristics that make Starship exceptional for Mars missions also make it potentially revolutionary as a space station platform. And the more you examine the details, the more obvious it becomes that a Starship-based station wouldn't just be better than the ISS, it would be a completely different category of infrastructure. Start with the numbers. The ISS has an internal pressurized volume of approximately 916 cubic meters. That sounds large. And for a structure built module by module over 13 years of launches, it genuinely is an extraordinary achievement. Starship's internal volume in its current configuration is approximately 1,000 cubic meters. In a single vehicle, launched in a single mission, one Starship could deliver more habitable space than the entire ISS in one launch. But that's just the baseline. Because SpaceX could develop dedicated station variants of Starship, versions that remove the fuel tanks, landing systems, and propulsion hardware that a permanent orbital habitat wouldn't need, and replace all of that with additional living and working space. The volume potential grows dramatically. And then consider connecting multiple Starships together. 2 Starships docked end-to-end, 3 arranged in a triangular configuration. Or the concept that keeps appearing in aerospace engineering discussions, a wheel configuration. Multiple Starship vehicles arranged in a ring, connected by a central hub, slowly rotating in orbit. Why rotation? Because of artificial gravity. This is one of the biggest unsolved problems in long-duration human spaceflight. Extended weightlessness causes muscle loss, bone density reduction, fluid shifts in the body, vision problems, and cardiovascular changes. Astronauts returning from 6-month missions to the ISS often need weeks or months of rehabilitation before they can walk normally again. Rotation solves this. By spinning a structure in space, centrifugal force creates an outward push that mimics gravity. Walk toward the outer edge of a rotating wheel, and you feel weight under your feet. No space station has ever successfully implemented artificial gravity in orbit. A Starship wheel configuration could make it a reality for the first time in history. That's not science fiction. That's engineering with hardware that already exists. Enter Starship, and everything changes. To understand why Starship matters so much here, you need to understand what building the ISS actually required. The ISS was assembled over 13 years. It required 42 assembly flights, including space shuttle missions, Russian Proton rockets, and Soyuz vehicles. Astronauts performed 127 spacewalks during construction and maintenance, totaling over 800 hours of extravehicular activity. 15 nations contributed hardware, funding, and personnel. The result is breathtaking. But the process was extraordinarily complex, extraordinarily expensive, and took over a decade to complete. Now consider the Starship approach. A Starship habitat works differently from the start. Instead of 42 flights to assemble a station, a Starship-based infrastructure could potentially be functional after just a handful of launches. The orbital assembly requirements drop dramatically. The spacewalk requirements shrink. The coordination complexity decreases. This isn't just about speed, it's about cost. Every additional launch adds risk. Every additional docking operation is an opportunity for failure. Every additional spacewalk exposes astronauts to the hazards of the space environment. Reducing the number of operations required doesn't just save money. It fundamentally changes the risk profile of the entire project. And here's the economic angle that ties everything together. Starship is designed to be fully reusable. Both the Super Heavy booster and the Starship upper stage are meant to be caught, refueled, and reflown, potentially within hours. The cost per kilogram to orbit for a fully reusable Starship is projected to be dramatically lower than any existing launch vehicle. Lower launch costs mean more launches. More launches mean faster construction. Faster construction means a replacement station could be operational years sooner than any traditional approach could achieve. The math changes completely. But Starship isn't ready yet, and that's the critical problem. Here's where the story gets complicated. Because everything described above depends on Starship actually working, reliably, repeatedly, and safely. And right now, it doesn't, not yet. Starship has made remarkable progress. The Integrated Flight Test Program has produced dramatic results, including the successful catch of the Super Heavy booster by the Mechazilla Tower arms at Starbase, an achievement that genuinely shocked the aerospace industry. But between early successes and operational reliability, there's a long road of engineering work still ahead. 3 specific technical challenges stand between Starship and a space station future. First, orbital refueling. A Starship-based station would need regular resupply missions, but for deep space applications and long-duration station operations, Starship needs to be capable of transferring propellant between vehicles in orbit. This is a technically demanding operation that has never been done at this scale. SpaceX is working on it actively, but it hasn't been demonstrated yet. Second, rapid reusability. SpaceX's cost projections depend on Starship being turned around quickly between flights, not maintained for weeks or months between missions. Achieving true rapid reusability requires solving thermal protection system durability, engine inspection efficiency, and propellant loading speeds simultaneously. The company is making progress, but progress isn't the same as proven capability. Third, reliable operations. Before NASA or any commercial customer commits to a space station architecture based on Starship, they need consistent, predictable performance over dozens of flights. Not a handful of successful tests. Dozens of routine operations. SpaceX has a track record of solving hard problems faster than most people expect. The Falcon 9 went from its first successful launch to routine operations in a relatively short time frame. The same pattern emerged with Crew Dragon. But Starship is orders of magnitude more complex than either of those systems. The question isn't whether SpaceX will solve these problems. Most aerospace analysts believe they will. The question is when, and whether that timeline aligns with the ISS retirement window. The geopolitical dimension nobody wants to say out loud. There's one more layer to this story, and it's the one that adds the most urgency. China's Tiangong space station reached full operational status in 2022. It's currently hosting a rotating crew of 3 taikonauts. It's being expanded with additional modules, and China has explicitly stated its intention to invite international researchers aboard, positioning Tiangong as a global scientific platform. Sound familiar? The ISS was the symbol of post-Cold War international cooperation. It was America's most visible demonstration of leadership in space, not just through technology, but through diplomacy. Through the ability to bring allies together around a shared mission. If the ISS retires in 2030 and no American-led replacement is operational, China's Tiangong becomes the only continuously crewed space station on Earth. Not by default, but by strategy. China has been building toward this moment for decades. And here's the detail that adds a sharp edge to this story. Russia, America's original partner on the ISS, has been gradually distancing itself from the program. Relations have deteriorated. The long-term future of Russian participation in ISS operations is genuinely uncertain. The geopolitical landscape that produced the ISS no longer exists. The next generation of space infrastructure will be built in a very different world, one where the competition isn't between government programs alone, but between entire national visions for what humanity's future in space should look like. The stakes of getting the ISS replacement right are far higher than most people realize. This isn't just about science. It's about who leads the next chapter of human civilization beyond Earth. Set aside the geopolitics for a moment, because there's something genuinely exciting buried in this story. A Starship-based space station wouldn't just be bigger than the ISS. It would be functionally different in ways that could transform what humans actually do in orbit. Think about the ISS layout. It's a series of connected cylinders, individual modules attached over years, creating a somewhat linear structure with limited interior flexibility. Moving between sections requires navigating narrow corridors. Large equipment is difficult to move or reconfigure. The station's layout is essentially fixed, determined by the sequence in which modules were launched and connected. A Starship habitat is different from the start. The full diameter interior of a Starship vehicle is large enough to stand upright with room to spare. With purpose-built station variants, you could have proper rooms, not just compartments or racks, actual differentiated spaces for laboratories, crew quarters, exercise facilities, medical bays, and observation areas. And then there's the spaceport concept. Multiple Starship stations connected to a central hub could function not just as a research platform, but as a true orbital waypoint. A location where vehicles traveling to the Moon, to Mars, or to commercial destinations in cislunar space could stop, refuel, exchange crew, and continue their journeys. Cargo, moving between Earth and deep space, would pass through this hub. Private missions could use it as a staging point. Scientific expeditions could depart from it. The ISS is a destination. A Starship station complex could be an infrastructure node, the orbital equivalent of an international airport. The difference in scale and function isn't incremental, it's transformational. And that's the vision that makes this moment so important. Because the decisions being made right now, about funding, about architecture, about which companies get support and which concepts get abandoned, will determine what that infrastructure looks like for the next 50 years. The real race, and who's actually winning. So where does this leave us? The ISS has less than 5 years. The commercial race has no clear winner yet. China is ahead of where most Western analysts expected. And Starship, the wild card, is advancing faster than its critics predicted, but slower than its advocates hoped. Here's the honest assessment. No single solution is clearly winning right now. Vast is closest to an operational station, but Haven 1 is small, and scaling it into a true ISS replacement takes time. Axiom is experienced, but dependent on the very station it's trying to replace. Orbital Reef has vision. But Blue Origin's history of slower-than-promised development creates legitimate questions about timeline. Starlab is focused, but hasn't yet demonstrated the flight heritage needed to build confidence. And Starship? Starship is the most powerful, long-term option. But it's also the one that requires the most additional development before it can serve as a station platform. The realistic scenario is a bridging strategy. One or more smaller commercial stations, probably Vast or Axiom, come online around 2028 to 2030, providing continuity of human presence while Starship matures. Then, in the mid-2030s, a larger Starship-based infrastructure begins to take shape, potentially initially as a cargo and logistics hub before evolving into a full habitat. That's not a single dramatic moment. It's a transition, a generational handoff from one era of space infrastructure to another. But here's the thing about transitions. The companies and nations that position themselves correctly during the transition period, that build the relationships, the experience, the hardware, and the operational knowledge, are the ones that dominate the era that follows. SpaceX understands this. That's why, even as Starship reaches for Mars, the company is deeply embedded in every commercial station program running today. They're the launch provider for Vast. They're the crew transport for Axiom. They're building the Artemis lunar lander on Starship. That strategic position wasn't accidental. It was engineered. And that might be the most important thing happening in space right now. More significant than any single launch, any single test, any single milestone. The foundation of humanity's future in orbit is being built right now, quietly, incrementally, but unmistakably. The ISS is dying. But what replaces it could be something far more extraordinary than anything that came before. The only question left is whether we'll be ready in time. The ISS gave humanity 27 years in orbit. What comes next could last a century. If this analysis helped you think differently about what's at stake, hit like, share it, and subscribe to The Space Brief. Drop your take in the comments. I read everyone.